This engine is a huge chance for the shipping industry to clean up its act.
Have you ever wondered why ships, despite carrying thousands of tons, move so slowly compared to cars or airplanes? The answer isn't just about size. It's a story of physics, engineering, and centuries of design choices. Today, we dive deep into why ship engines run slower than any other engine. The giant vs. the speed. Imagine a massive cargo ship, longer than 3 football fields, gliding through the ocean. It can carry enough goods to fill hundreds of trucks, yet its speed rarely exceeds 25 knots, about 46 kilometers per hour. Compare this to a car, racing at 200 kilometers per hour, and it feels painfully slow. But here's the twist. Ships don't need to be fast. Their engines are designed for power, efficiency, and durability, not speed. Pushing a ship too fast will consume enormous fuel, damage the engine, and even create dangerous stress on the hull. Ship engines are built to move slowly but move immense weight efficiently over thousands of miles. Unlike cars or planes, they operate continuously for days or weeks, so longevity and fuel efficiency take priority over high speed. The water vs. the air. Cars race on roads and planes slice through air, both low-resistance environments compared to water. Water is 800 times denser than air, which makes moving through it far harder. Every extra knot of speed demands exponentially more energy. Here's a fun fact. Doubling a ship's speed doesn't double fuel consumption. It quadruples it. That's why even powerful engines cruise at slow speeds. Unlike cars, which burn fuel for quick bursts, ships must burn it steadily over months-long journeys. The ocean isn't forgiving either. Waves, tides, and currents resist movement. If a ship tried to go as fast as a plane relative to its size, the engine would overheat, fuel costs would skyrocket, and structural stress could literally tear the ship apart. So, ships go slow to survive the long, harsh journey. The engine design. Ship engines are engineering marvels, but they're completely different from car or airplane engines. Most large ships use diesel engines, some as tall as a 5-story building, designed for torque, not speed. Torque is a twisting force that moves heavy objects. Imagine trying to push a giant boulder versus a bicycle. The engine doesn't need to spin fast. It needs to push enormous mass steadily. That's why ship engines rotate at just 100 to 150 revolutions per minute (RPM), while a car engine can spin at 3,000 revolutions per minute or more. These engines are also huge and heavy. Their size allows them to generate massive power without overheating. They are often directly connected to propellers without gears, reducing mechanical losses and increasing efficiency. Interestingly, the slower rotation also makes engines incredibly durable. Some ship engines can run continuously for 20 to 25 years with regular maintenance, something impossible for a car or plane engine. So, while the RPM is low, the output is enormous, enough to move 200,000 tons of cargo across oceans, silently, steadily, and safely. Fuel efficiency. Fuel is a ship's lifeblood, and it's expensive. Running a ship engine faster would burn fuel exponentially faster, making shipping goods uneconomical. Slow speeds allow ships to achieve optimal fuel efficiency, sometimes carrying cargo thousands of miles for a fraction of what a faster engine would consume. Ship engineers often calculate the sweet spot where speed meets fuel economy, usually far below the engine's maximum potential. For example, a container ship might have a top speed of 30 knots but cruises at 20 knots. The small reduction in speed saves millions of dollars in fuel annually while reducing wear and tear on the engine. This principle has led to the modern term slow steaming, a strategy used by shipping companies to reduce costs, emissions, and engine stress while keeping global trade moving smoothly. Propeller physics. A ship's propeller is more than a spinning fan. It's a carefully engineered powerhouse. Propellers work best at lower speeds because water is dense, and spinning them too fast causes cavitation, bubbles forming and collapsing on the blades. Cavitation isn't just noisy, it erodes propeller metal over time and reduces thrust. That's why even the most powerful ship engines rotate slowly, to maximize propulsion while protecting the propeller. Additionally, larger propellers turn slower, creating massive thrust per rotation. This is opposite to a car, where tires spin fast for speed. In water, bigger and slower winds over smaller and faster. So, slow engine speed, combined with massive propellers, is a perfect recipe to move enormous ships efficiently and safely through the ocean. Longevity and reliability. Ships travel thousands of miles over open oceans, often in extreme conditions. They can't afford engine failures in the middle of the Atlantic. Slow engines reduce stress on components, increase reliability, and ensure continuous operation for days or weeks. Unlike cars, which can be serviced every few thousand kilometers, a ship might go weeks without major maintenance. A slow, steady engine reduces the chance of overheating, metal fatigue, or catastrophic failure. This longevity is essential not only for cargo ships, but also for naval vessels, icebreakers, and tankers. A ship engine failure in the middle of the ocean can mean weeks of delays, massive financial loss, or even life-threatening danger. Therefore, ship engines are intentionally slow, trading speed for unmatched durability, reliability, and safety. Historical lessons. The design of slow ship engines isn't new. Steamships in the 1800s already used low-speed engines for efficiency and reliability. Early engineers quickly realized that pushing engines too fast led to frequent breakdowns and poor fuel efficiency. Diesel engines replaced steam, but the principle remained: slow, powerful, reliable beats fast and fragile. Modern ships still follow this rule, blending new technology with centuries of maritime wisdom. Even high-tech nuclear-powered ships, like aircraft carriers or submarines, use slow, high-torque engines to move silently, efficiently, and safely. So the next time you see a massive cargo ship crawling across the horizon, remember, its slow speed is a carefully calculated choice, a balance of physics, economics, and engineering brilliance. Conclusion. Ships run slower than any other engine not because engineers can't make them fast, but because the ocean demands power, efficiency, and reliability over speed. Dense water, massive weight, cavitation, fuel costs, and engine durability all combine to dictate slow, steady propulsion. Next time you watch a container ship inch along the horizon, remember, it's not slow, it's strategically unstoppable. Every slow rotation of its colossal engine is a testament to centuries of engineering, physics, and wisdom, quietly moving thousands of tons safely across the globe. Ships are proof that sometimes slow is the ultimate speed. Thanks for if you enjoyed this video. Don't forget to hit like, share, and subscribe for more updates.